y prime minus y equals 0 with y of 0 equals 1. In how many ways can you solve this equation? So now that we learned so many methods to solve differential equations, let's use them to see how we solve this given equation. So we have a linear differential equation, first order, very simple. The coefficients are 1, -1, is homogeneous because it's equal to 0. So let's try with the first method. Method 1, separation of variables. So we would say dy dx minus y equals 0, which means dy dx equals y. So what I'm going to do is I'm going to multiply by dx both sides, so we get dy equals y dx. And then I'm going to divide by y both sides and get dy over y equals dx. We separated the variables, we integrate both sides, and we get ln of absolute value of y equals x plus c. We raise everything to e, so e to ln of absolute value of y equals e to x plus c. We use properties of exponents, where if the base is the same with the base of ln, we get absolute value of y equals, we use properties of exponents and say e to the x times e to c. So absolute value of y equals e to c, it's a constant, so it's c e to x, and y equals plus minus c e to the x, which means y of x it's equal to c e to the x. We just absorb the plus minus into the constant. And we got this solution. When we divide it by y, we might have lost y equals 0 as a solution, but if c equals 0, we do get that solution. So it is embedded in our y of x equals c e to the x. Method 2, linear equations. So our equation, y prime minus y equals 0, let's try to solve it using the strategy for linear equations. The linear equations method was multiply both sides by e to the power of integral of p to the x. P to the x was the function or the constant in front of y, so that means -1 dx, because we assume our independent variable is x. So we get e to negative x. So we multiply both sides and we get e to negative xy prime minus e to negative xy equals 0. Now the left side was multiplied by e to negative x to create a perfect derivative, and the derivative is of the function y e to negative x. So you can double check by doing product rule. So y prime e to negative x, it's this term, and then plus y copied and e to negative x prime, it's negative e to negative x. So it was done right, equals 0. Now we integrate both sides with respect to x, and we get y e to negative x equals 0 plus a constant. So we get this constant, which means y of x equals c e to the x, because we divide by e to negative x both sides and we change it into positive exponent. So we got the same solution as before, right? We also have an initial condition, so I should have done that as well. So y of 0 is given to be 1. That means c equals 1, so y of x is actually e to x, the final answer. So the same thing happens here. Y of 0 equals 1, so c equals 1, which means y of x is e to the x. So the second method and the first method produce the same thing. Let's think of the third method, the operators method. So we are going to write y prime minus y as d minus 1 applied to y equals 0. Now d is replaced with r, so r minus 1 equals 0, which means r equals 1. It's a simple solution, so that means y of x equals c e to the x. So the same thing as before with the initial condition. So we got the same answer. Another method, Laplace transform. So y prime minus y equals 0. We apply Laplace transform to both sides, so we get Laplace transform of y prime minus Laplace transform of y equals 0. Laplace transform of y prime, it's sy of s minus y of 0 minus Laplace transform of y, we can write it y of s equals 0. So we learned these methods. Now I'm not reteaching them, I'm just using them. They are already known. So we factor out y of s and we get s minus 1 minus y of 0 was given to be 1, so minus 1 equals 0. This is basically the reason why I gave an initial condition, so that we can apply Laplace transform. Without an initial condition, we cannot apply Laplace transform. So y of s equals 1 over s minus 1, which means y of x is inverse Laplace transform of 1 over s minus 1. And if you remember the tables, or you can look in the table, you're going to see that it's e to x. So in this case, we don't get the c anymore because the c is already computed when we do Laplace transform. Method 5. So we want to solve y prime minus y. Let's do power series. So y prime minus y equals 0. So in order to do power series, we start with y of x equals sum as k goes from 0 to infinity of a sub k, a to k, x to k. And so y prime of x, it's sum as k goes from 1 to infinity, a sub k and k x to k minus 1. We used power rule. Now replace both of them into the equation star. K goes from 1 to infinity of a sub k times k x to k minus 1 minus sum as k goes from 0 to infinity a sub k x to k equals 0. The goal is to get from these two sums only one sum equal to 0, and when and a power series equals 0 when each coefficient equals 0. So in order to do that, first we need to have x to the generic power x to k. So the second one already has x to k, but the first one doesn't. So in order to do that, we have to add 1 everywhere we have k except here. So we go sum, and then we have a sub k plus 1 times k plus 1 x to k. So when the first term of this series, it's actually a sub 1. To obtain a sub 1, now that we change the k into a k plus 1, we'll have to start at 0, right? Because now a sub 0 plus 1 is going to give us a sub 1, and then 0, and then 0. So we have to be very careful when we add 1 to all the terms in yellow. We have to subtract 1 from the bottom, from the lower boundary, minus sum as k goes from 0 to infinity of a sub k x to k equals 0. So we notice that we have now both sums have started at the same point. We have the x to the k term, so we can put them together as sum as k goes from 0 to infinity, factor out x to the k, and then write the coefficients as a sub k plus 1 times k plus 1 minus a sub k equals 0. So the terms of a series equal 0 if each coefficient equals 0. So a sub k plus 1 times k plus 1 minus a sub k equals 0, which means a sub k plus 1 equals a sub k over k plus 1. So we got the recursive formula where we can say a sub 0 is the first term. And so if k equals 0, we get a sub 1 equals a sub 0 over 1, which is a sub 0. If k equals 1, we get a sub 2 equals a sub 1 over 2, which is a sub 0 over 2. If k equals 2, we get a sub 3 equals a sub 2 over 3, which equals a sub 0 over 2 times 3, which is a sub 0 over 6. If k equals 3, we get a sub 4 equals a sub 3 over 4, which is a sub 0 over 24. But we can notice that this is a sub 0 over 2 factorial, this is a sub 0 over 3 factorial, this is a sub 0 over 4 factorial. So, in other words, we can say that y of x equals sum, as k goes from 0 to infinity, of we had a sub k x to a k, so it's going to be a naught plus a1 x plus a2 x squared plus a3 x cubed plus a4 x to the 4 plus so on. But in our case, a naught, we keep it a naught, a1 it's a naught x, a2 is a naught over 2 factorial x squared, a3 it's a naught over 3 factorial x cubed, a4 it's a naught over 4 factorial x to the 4th, and so on. So we can factor out a naught and get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot, which gives us a naught times. I hope you notice that this is Maclaurin series of e to the x. So we got that y of x, it's a naught times e to the x. But a y0, it's given to be 1, which means if we go to y of x originally, which is the sum as k goes from 0 to infinity of a sub kx to the k, which is a naught plus a 1x plus a 2x squared and so on. If we replace with 0, we get a0 equals 1. So y of x equals e to the x, and we solved again the same equation with the 5th method. So we solved the same problem with 5 methods. Not all of them will work like this, but it's good to know more methods because you can double check your answers. And another reason is if one method doesn't work, you can always try another one. So I hope this helps.